we were talking about example 10.9 and looking at the rotational velocity. So we're going to go ahead and continue from there. We found that it was 31.4 radians per second. Now, I mentioned the rotational kinetic energy was in this form, and my inertia is actually going to be a little bit different here. So this is for a, a point particle. So this is for a point particle. And we can't use that because we have a rod, okay? We are approximating these helicopter blades as thin rods. So I'm going to go ahead and skip ahead because I put this in the wrong spot. That we want a thin rod, and it is going to be about which axis? Let's see. One end of the axis perpendicular to their length. Okay, so it's going to be perpendicular to their length. Okay, so that'll be right there. So let me see. Thin rod about axis through the end to the length, right? Make sure that I'm reading that right. One end perpendicular to their length, one end perpendicular to the length. Okay, so this diagram should have been earlier, but it has all of these moment of inertia of different objects. So if we have a hoop about a cylinder axis, if we have a hoop about any diameter, if we have a cylinder, a thin rod, a sphere, and so forth, it'll tell you exactly how to calculate it. So right now we are looking at a thin rod about axis through one end perpendicular to the length. So our I is going to be equal to our mass times L squared, which is the length of that rod, divided by 3. Okay, so ml squared divided by 3. So our I is going to be ml squared over 3. Okay, and again, that'll still be times 4 since they are all identical. Okay, so what we'll do is we'll have kinetic energy equal to 1/2 times 4 times ml squared over 3 times omega squared. Okay, so this gives us 2 over 3 ml squared omega squared. Okay, I'm going to move over here, 2/3. Our mass is 50 kilograms. Our length is 4 meters. Okay, and our omega is going to be 31.4 radians per second, and we're going to square that as well. So let me put all of this into my calculator quickly. Oops, times, not plus. 50 times 2/3. And I get a kinetic energy of 5.26 times 10 to the 5th, and this is going to be in joules. Okay. Whoa. So even though it's rotational motion, it'll still have units of joules. Okay, units of energy. Okay. All right. So now we want to find the rotational energy of the helicopter when it flies at 20 meters per second and compare it with the rotational energy in the blades. So let's see. The helicopter has a total loaded mass of 100 kilograms. So let's go ahead and say our mass now is, what was it? 1,000 kilograms. And we want to know the kinetic energy of this. And this is going to be 1/2 mv squared, whoops, where our velocity was given as 20 meters per second. So we're going to say 1/2 times our mass times our velocity squared. We're going to put that into our calculator. 0.5 times 1,000 times 20 squared. So we get 2.0 times 10 to the 5th joules. Now let's compare that. We have our blades that have a rotational kinetic energy of 5.26 times 10 to the 5th. And our helicopter with a loaded mass has an energy of 2.0 times 10 to the 5th joules. Okay, so comparing the two, this makes sense because if this number was greater than the kinetic energy of those blades, then the helicopter wouldn't be able to lift and get up and fly. Okay? All right, let me move that over there. Okay, moving on. Looking at moment of inertia. I'm not sure what I was gonna do here, but I'll talk about it anyway. So our moment of inertia, we can look at it in different ways. So we have two barbells here, and each of these weights here have some mass, and we are turning it with some omega, okay? And in this case, we're rotating it about this axis, which is about half of this weight system, okay, our system of interest. And it is going to have a different moment of inertia than this one over here. Okay, so inertia, we can also do this for any type of shape, so it doesn't have to be perfectly thin rod or a cylinder or a sphere or anything like that. We can also have take an infinitesimally small piece of mass, and we call that dm, and this equation will then become I equals the integral of r squared dm. Okay? All right, again, these are our different objects, the most moment of inertias for these objects. Okay? Feel free to look over them. They, will pop up in your homework, so just familiarize yourself with this diagram, okay? All right, let's do another example. A 25 kilogram child stands at a distance r equals 1 meter from the axis of rotating merry-go-round. The merry-go-round can be approximated as a solid uniform disc with a mass of 500 kilograms and a radius of 2 meters. Find the moment of inertia of this system. Excuse me. So what we'll do is we will go ahead and remember that the moment of inertia is going to be the sum of each moment of inertia of each object in the system. Okay, so that's our first step, is to understand that. Then we need to break this down. So it states that we have a uniform solid disk, and that's going to be the merry-go-round. So I'm going to go ahead and look here, so here we have a disc and it's rotating about its axis, which makes sense because our merry-go-round would be rotating this way. Okay, so we'll have a moment of inertia of the solid disk, and so that'll be mr squared over 2. And this is going to be, hold on, this is going to be our inertia of the solid disk. Let me just write that down. That way I know what is going on. So I have I sub d. Okay, and then I have of the child, and in this case, because the child is so much smaller, has so much less mass, we're just going to say that he is a point mass on this system. Okay, so then we're going to have mr squared, and this is I sub child, I guess. Okay, so our total I is going to be the mass of the merry-go-round, 500 kilograms, times the radius of it, which is 2 meters, square that over 2, plus our mass of the child, which is 25 kilograms, times our radius, which is 1 meter. Okay, so it'll be 500 times 2 squared over 2, and then add 25. So our moment of inertia is going to be 1025, and this is in kilograms meters squared. Okay, this could also be 1.03 approximately times 10 to the third kilogram meters squared, whichever way you want to write it. All right, so now we are going to talk about torque, and that is going to be the turning or twisting effectiveness of a force. Okay, so, excuse me, let me get my pen out. When a force is applied to some point whose position is R relative to O, or the origin, the torque around O is, or the origin, is going to be tau equal to R cross F. Okay, and if we take that magnitude, the magnitude of a cross product is going to be those two values here, RF times sine of theta, or we can rewrite this as R perpendicular times F. Okay, and when we're trying to find the net torque, it's going to be the summation of all of the individual torques of the system. Okay, so let me go ahead and show you guys this figure here. So we have, all of these different forces that are being applied. So let's look at this one first. We have some force being applied to this system. It looks like a door. We have a door and a door hinge. Okay, so when we typically open a door, we tend to give it a force on the outer edge where like the door handle is, right? Because it's pretty easy to open that way. Now, if we do something different where we try to open the door towards the center or towards even the hinge here, it makes it a lot harder to open that door. Okay, and this is because of torque. Okay, so as we increase the radius or the position to where the force is being applied, we also call that the lever arm. Okay, so if we increase that value, our force being applied will be less. We won't have to use as much force, I should say. Okay, for the door to open. And this is also true with if we, use the force in a different direction. Okay, so I'll continue our discussion on torque in the next video.